Welcome to LNG, the not-so-new fuel. Let's explore this not-so-new fuel source. Liquefied natural gas, or LNG, is simply natural gas that's been cooled to around negative 162 degrees Celsius, turning it into a liquid to reduce its volume for easier storage and transport. However, it's extremely complex in the making. I'll walk you through the path from the raw gas to the cold liquid that is ready for commercial use. Liquefying natural gas shrinks its volume to about 1/600th of its original size. Once vaporized, its expansion rate is 600 to 1, and it becomes flammable when the methane concentration in air is between 5 and 15%. That's why every step in the LNG chain, from production to transport and storage, is precisely engineered for containment, fire prevention, temperature control, pressure regulation, and safety. Methane was first liquefied back in 1886, but it wasn't until 1918 that large-scale natural gas liquefaction began in the US, originally as part of helium extraction. Even then, it wasn't stored as a liquid until 1941, as global demand for natural gas grew and pipelines couldn't reach every corner of the world. LNG offered a new solution. Over the decades, liquefaction and shipping evolved into a full-scale global supply chain. Today, massive LNG plants operate multiple liquefaction trains in parallel, each one transforming pipeline-quality gas into export-ready LNG. The journey of natural gas begins at the wellhead, where it's separated from water, solids, and other impurities before flowing through gathering lines to processing plants. First, contaminants are stripped out, the gas is dried, and it's compressed into high-pressure transmission pipelines. By the time it reaches an LNG plant, the gas is considered pipeline quality, but it's still not clean or dry enough for cryogenic service. The feed gas in LNG production is mostly methane, usually over 90%, with small traces of ethane, propane, butane, and nitrogen. But to keep the liquefaction process running smoothly, the gas has to meet very strict purity specifications. Even tiny amounts of CO2, H2S, water, mercury, or heavier hydrocarbons can restrict or damage the cold box heat exchangers. That's why operators are constantly monitoring the pre-treatment systems, because even a slight deviation in gas quality can cause huge operational inefficiencies. The first major pre-treatment step is called sweetening, where acid gases like CO2 and H2S are removed. This happens in an amine system. As gas flows upward through an absorber tower, a special amine solution flows down in the opposite direction. The amine selectively captures the sour gases, leaving cleaner, sweet gas at the top. The used or rich amine is then sent to a regenerator, where it's heated to release the absorbed CO2 and H2S. Once cooled, the regenerated lean amine is cycled back into the loop. In the field, this unit is a critical safeguard. If the amine system underperforms, it can lead to CO2 freezing in the cold box or corrosion problems later on. So operators watch it closely, keeping tabs on temperatures, flow rates, and the amine concentration in the system. After sweetening, the next priority is removing moisture. Because at LNG temperatures, even tiny amounts can freeze into ice or form hydrates, which can block valves and exchangers. To prevent that, the gas is dried using molecular sieve beds. These towers are packed with a crystalline material that absorbs water down to incredibly low levels. This system runs in cycles. While one bed is online drying the gas, another is being regenerated with heat. For operators, it's all about keeping an eye on bed temperatures, pressure drops, and breakthrough timing, because any issue here flows straight into the main cryogenic heat exchanger. Even after removing water and acid gases, heavier hydrocarbons can still pose problems. Components like propane, butane, and heavier NGLs increase the risk of freezing and can throw off the mixed refrigerant balance. Most LNG plants use a cold gas separator or heavies removal column to strip out heavier hydrocarbons before the gas enters the colder sections of the cold box. Some designs go further by integrating NGL recovery with LNG production, allowing efficient removal of ethane, propane, and butane while still delivering a clean, stable feed to the liquefier. Once the gas is clean and dry, it enters the heart of the LNG plant, the main cryogenic heat exchanger. Different technologies are used depending on the plant design. Propane, pre-cooled mixed refrigerant, pure mixed refrigerant systems, cascade cycles, or nitrogen expanders are among the most common. While the methods vary, they all serve the same purpose, gradually cooling the gas in controlled steps from ambient temperatures down to cryogenic temperatures, all while carefully managing pressure, flow, and gas composition. In a typical mixed refrigerant liquefaction train, propane and isobutane provide the first stages of cooling. High-pressure ethylene then manages the mid-range temperatures before methane and nitrogen take over in the final, ultra-cold cryogenic stage. The mixed refrigerant is continually compressed, cooled, and expanded so that its boiling curve mirrors the cooling curve of the natural gas. That tight temperature match is what makes the liquefaction process efficient. Beneath the process are the fundamental gas laws tying pressure, temperature, and volume together. As LNG leaves the main cryogenic heat exchanger, it is still at elevated pressure, but when it passes through the discharge control valve or Joule-Thomson valve, the pressure drops close to atmospheric. This causes a small fraction of the LNG to flash and vaporize. This vaporized gas absorbs latent heat and cools the remaining liquid even further. This final flash creates the subcooled, stable LNG that is sent to storage. For an operator, this isn't about theory or equations. It's about monitoring the trends. It's about watching the numbers, suction and discharge pressures, temperature gradients in the cryogenic heat exchanger, levels in the cold gas separator, refrigerant composition, and LNG quality. All of it tells you whether liquefaction is stable, efficient, and safe. Once the LNG is fully subcooled, it's sent through heavily insulated or vacuum-jacketed pipelines to massive storage tanks. In designs without full containment, these tanks have an inner shell made from 9% nickel steel to safely hold the LNG at cryogenic temperatures. Around that inner tank, layers of perlite insulation, sometimes padded with nitrogen, to help block out moisture and keep temperatures stable. The outer tank, usually carbon steel, provides structural strength but isn't designed to hold liquid if the inner tank were to fail. Because of that, the entire tank sits inside an engineered dike or near an impoundment basin that is designed to hold 110% of the tank's storage capacity should it fail. Inside the storage tank, pressure is kept just above atmospheric, with the LNG held near its natural boiling point around minus 162 degrees Celsius. Any boil-off gas from normal heat gain is managed carefully. It might be used as fuel, sent to reliquefaction, compressed back into the pipeline, or, if needed, safely burned off in a flare or thermal oxidizer. From there, LNG moves to the loading side, whether it's truck racks, bunker vessels, or large LNG carriers. The systems, safeguards, and procedures used for transfer are well established and familiar to anyone experienced in LNG loadout operations. When you stand on a manifold or in a control room, it's easy to focus only on today's transfer or today's loading window. But every cubic meter in that tank has already survived a long chain of operations. Gathered at the wellhead, separated from liquids and solids, transported through pipelines, followed by sweetening, drying, heavies removal, cryogenic liquefaction, and careful storage. The logistics are quite a feat, but pale in comparison to the safety required from start to finish. That's why people who work in LNG tend to be detailed and safety-driven. We know that if you respect the chemistry, the gas laws, and the operating envelopes, LNG is a very predictable and very manageable product, and that respect for the process and for the hazards is what keeps this industry running safely, day after day, load after load, and year after year.